before moving into the methods of computing partial fractions, I need to highlight two important points. Okay, so the first one is, now if first one is, now as I explained before, we need to check whether it is improper, and if it is improper, as I did in these examples, we should do the long division. And these steps, the steps that I'm going to explain, are valid for the proper rational function. Now, what I mean by rational is a something which has a numerator and a denominator, and in both numerator and denominator you have polynomials. Okay, so the methods that I am going to explain next holds only for these proper rational functions. That is the reason why we check whether it is improper or not, right? Now, what I mean by proper is that the degree of the numerator is less than the degree of the denominator, and improper is the opposite direction, right? So if the degree is greater than the if the degree of the numerator is greater, we call it improper, and if it is not, we call it as proper. So these methods that I'm going to explain are only valid for proper rational functions, right? So now see, for these improper rational functions also, once we do the long division, it will give you proper rational functions, right? See, in both these cases, the degree of the numerator is less than the degree of the denominator. Now, if you have a single polynomial, that means if the degree of the denominator is 1, we don't simplify it any further, right? So we just keep this one as it is, and we focus mainly on these rational functions which are proper, right? These we obtain these proper rational functions as a result of the long division, right? So that's the first step that I want to highlight. All these methods are for the proper rational functions. And the second step that I want to highlight is this theorem. Now, we are not going to discuss a proof for this theorem, but you should understand the statement of this theorem. I mean, what it means by this theorem, you have to understand the proper correct meaning of this theorem. Okay, right. So here what it says is, every polynomial can be factored as a product of linear factors and irreducible quadratic factors. First, let me explain what you mean by an irreducible quadratic factor is. Say for example, if we have something like this, x squared plus 2x plus if you consider these polynomials, you can see that this one can be factored out as x plus 1 times x plus 1. This one can be factored out as x plus 1 times x plus 2. But this one you cannot factorize it like that. Okay. Now, factoring out means you are finding the roots, right? So for all these polynomials, if we plot the graph, it will be this. The first one will be something like this. So the there will be a single root touching the x-axis, and for this one it will be something like this, which cross the x-axis at 2 points, -2 and -1, and this one will have a will not have any intersections with the x-axis. So basically this does not have any root. So the point that I want to mention here is that you cannot factorize this polynomial into linear factors like this. And what do we mean by a linear factor? That means a polynomial which doesn't have any higher degree x terms. Like the highest degree of x in a linear polynomial is 1, right? It does not have any higher degree polynomials like x to the power 3 or x to the power 4 or so on, right? So for these two polynomials we were able to factorize into linear factors, but not this one. So when we are given with a certain polynomial, a second degree polynomial, now keep in mind all these polynomials are of second degree, right? So how do we see whether we can factorize it or not? This is the theorem, this is the condition that we should check to see whether it is possible for a linear factorization. So if this holds true, if this b squared minus 4ac term is less than 0, you cannot factor it out for linear factors. So for example, if we take the first polynomial, the value of a is 1. Now see, this is the way they have given the polynomial. The coefficient of x squared is represented by a, coefficient of x is represented by b, and the constant term is given as c. So in the first polynomial, the value of a is equal to 1, b is equal to 2, c is equal to 1, right? Therefore b squared minus 4ac will be equal to 0, right? And for this, see, it is not negative, right? It is 0, so linear factorization is possible, and we have already found the linear factors. And in this case, the value of a is equal to 1, b is equal to 3, and c is equal to 2. Therefore b squared minus 4ac will be equal to 1, right? So that means this is also not negative. So this condition does not hold true. That means we can do the linear factorization, and we have already found the linear factors as well, right? But in the third example, see, a is equal to 1, b is equal to 1, c is also equal to 1. Therefore b squared minus 4ac will be equal to 1 minus 4, which is equal to negative 3, and that is less than 0, right? So this condition holds true. In other words, this cannot be factored into linear factors. And if we can't factorize this second degree polynomial, we call that polynomial as an irreducible polynomial. Okay, we call it as an irreducible polynomial, right? Okay, now this is not the theorem that I have written in blue color. This is just the meaning of an irreducible factor, right? Now quadratic means of degree 2. So irreducible quadratic factor means a polynomial of second degree which we cannot find any linear factors, right? So that's the meaning of this sentence. And now I am going to explain the meaning of this theorem that I have written in blue color, right? So in the theorem it says every polynomial can be factored as a product of linear factors and irreducible quadratic factors. So this is the theorem, and we are not going to discuss the proof of that theorem. Okay, we just understand the meaning and apply it in our theory, right? Right, so what does it say? Any polynomial. Okay, so no matter what polynomial you give, it can have any degree, right? So it can either be a quadratic polynomial, or it can be a third degree polynomial, or it can have any degree as required. Okay, so the theorem says no matter what degree it has, that polynomial can be written as, now let's say if I have a polynomial like this, x to the power 10 plus, also this can have some coefficients, something like this, right? And polynomial is not an infinite term, right? So it will have a finite number of terms, and it is not a must to have a constant at the end. Okay, it can be even 0, right? So no matter what degree it has, the theorem says you can write this polynomial as a product of a certain thing, and that certain thing is as a product of linear factors and irreducible quadratic factors, right? So linear factors means the ones of this format, ax plus b, right? And quadratic factors means this one, right? Say for example, if I choose a particular case, if we have this polynomial x squared, not x squared, x to the power 4 minus 16, right? You can write it as, now this, from this theorem we cannot find the linear factors, right? This doesn't give any method to compute those factors, right? It just mentioned that you will definitely have linear factors. You will definitely have such a factorization with the combination of linear factors and irreducible quadratic factors. But it is not a must to have both of these things, right? At least it will contain at least one of these two things. It can have both these terms or one out of these two things, right? It is not a must to have both at once. But in this example that I am going to tell, it has both linear factors as well as irreducible quadratic factors. Now, to find these quadratic factors, we will need some knowledge in algebra, right? And so, what I want to stress here is the theorem does not give a method to compute those factors, okay? Right. So, if we consider this one, x to the power 4 minus 16, then the mentioned factors will be x minus 2 times x plus 2, x to the power 2 plus 4. See, these two are linear factors and this is a irreducible quadratic factor, right? This has a degree 2 and the b squared minus 4ac value is less than 0 in this case. And the reason for mentioning this theorem is because, now remember, in the previous video I mentioned we are not going to simplify this portion any further, but we are doing it for this one, right? Reason is see, this is a linear factor, okay, but this is not, right? And from the theorem it says you can separate this one into linear factors as well as irreducible quadratic factors. So our main goal is to simplify this given big thing. Once we do the long division, then simplify these remaining rational functions until you have linear factors or irreducible second degree polynomials, right? We should do this until you reach linear factors or irreducible quadratic factors. Okay, so that should be that is our prime goal of computing the partial fractions, right? So, and then with all these details in mind, now this is not a like a difficult thing, right? I explained very simple two very simple conditions, right? Here it says we are now the methods. I didn't mention those methods yet. Okay, so those methods will be valid only for the proper fractions, proper rational fractions. And then in the theorem it says no matter what polynomial you have, it can be reduced down to linear factors. I mean reduced down as a product of linear factors and irreducible quadratic factors. So in the method of partial fractions, what we do is we try to simplify these denominators of proper rational functions so that it reach these linear factors and irreducible quadratic fractions. Factors. Okay. So in the next video, I'll give the 4 categories of partial fractions.